And at last, we're getting onto heuristics. So heuristics, it's some guidelines towards design, and essentially you can apply these to whatever situation there is, and when you apply them, you really have to test it. So it's not going to apply it in all situations, or it might apply at the limits of the case or something like that. So essentially, you should also be doing your simulation and checking if that heuristic applies in the case you're applying it to. Right, so let's, oh dear, no, why is it not? Maybe I have to make this the active screen. Yes. Right, so recalling process operations in process synthesis, we had a chemical reaction, mixing and recycle, separation, temperature, pressure, and phase change, and task integration as the 5 steps. This lecture deals with the rules that expedite the selection and positioning of processing operations as flow sheets are assembled. So it's essentially the first part of your design project where you need to develop a flow sheet. And you saw in task integration, that was, I've got a pointer that you can see, I'm sure, that in the task integration, there were quite a lot of design decisions you had to make. And without any experience, those design decisions might be difficult. So the rules are based on experience and hold in general, but should be tested, for example, by simulation to ensure that they apply in that specific application. That's exactly what I said just now. Later, we'll see how algorithmic methods, those are just the calculations, are used to improve on design decisions. Right, so here's heuristic 1 at last. But before we go on to that, let me just have a look at those comments. Oh, there's only one. What content will the test be based on? The test, right, that is a good question. The test is going to be based on going through those 5 steps of process synthesis. So you won't have too many of these heuristics as background, but you would still be able to go through those 5 steps. And it's just a matter of, let me go back one. Can I make that the, yes. That essentially you're going through these first 4 where you only use blocks, and it's only on number 5 where you actually show equipment. So I just want to see that you can do those 5 steps using ordinary logic and knowledge of vapor-liquid equilibrium. In other words, the separation, that you understand how light components will go to the top of a distillation column, heavy components go to the bottom of a distillation column. Temperature, pressure, and phase change, that you show those as blocks and not as equipment, and eventually show equipment in task integration. So the test is going to go through this whole process of process synthesis. Right, so let me get back to this as that's what Angelo thinks of my test. He just left the session. Okay, heuristic 1. Select raw materials and chemical reactions to avoid or reduce the handling and storage of hazardous and toxic chemicals. We saw that we saw heuristic 1 being applied in the vinyl chloride monomer process, where we try to remove hydrochloric acid as quickly as possible. It is hazardous and toxic, and you remove it first. It also happens to have the lowest boiling point. In other words, it had the highest vapor pressure, and that was also a good reason to remove it first. So an example is the manufacture of ethylene glycol, and that formula, CH2CH2, bridged by an oxygen. And that plus water will make ethylene glycol. But both reactions are highly exothermic. They need to be controlled carefully. Water spill into an ethylene oxide storage tank could lead to an accident similar to the Bhopal incident, where this cloud of toxic gas came off a plant due to a similar sort of incident, and that toxic gas went over drifted over a heavily populated area, and many people lost their lives in that incident. So often such processes are designed with two reaction steps, with the storage of the intermediate to enable continuous production, even when maintenance problems shut down the first reaction operation. So if you've got a really complex, a long process thing without a process, a long process, a complex process without any storage in between, any breakdown in your equipment will cause the entire process to stop. But if you have an intermediate, you would rather, and it is possible to store it, you would rather store it. So that's what we're saying over here. You would, if possible, you would store. But when it is a toxic chemical like that, it is dangerous to store. So then you try something else, and we try and avoid forming that ethylene oxide as an intermediate. So you use chlorine and caustic in a single reaction step, and you make it directly, and plus sodium chloride. As the ethylene oxide is formed, react it with carbon dioxide and form ethyl carbonate, a much less active intermediate that can be stored safely, and hydrolyzed to form the ethylene glycol product. Those are the two options you can use. Right, so that was heuristic 1. Heuristic 2, use an excess of one chemical reactant in a reaction operation to completely consume a second valuable, toxic, or hazardous chemical reactant. So I'm going to start writing on this. Oh, no, I can't. No, I'm gonna write on my PowerPoint. So I must get to my PowerPoint. No, that doesn't work. PowerPoint, this one. No. This one. Yeah, I'm trying to write on the screen.
No, I just have a question on heuristic 1.
Yeah.
Does choosing a different reaction step fall underneath that heuristic, or is it just a case of if you have a corrosive or toxic chemical, you separate it immediately?
Repeat that. If you
for heuristic 1, I understand that if you have a very toxic or hazardous chemical, you separate it as soon as possible. I just want, when you were discussing about alternatives to the two-step ethylene process, does that fall underneath heuristic 1, or is that just extra information?
It is falling under heuristic 1. So if you can avoid it, so I think the heuristic says, let's just see if I can go back. Let's go back. Oh, I see you can't see this thing that I'm showing at the moment. I'm showing the original. So let me put to avoid or reduce the handling and storage. So in the case of vinyl chloride monomer, we reduced it by removing it as quickly as possible. we reduce the handling. If we removed it later, we would have had 2 distillation columns that include the handling and storage of hazardous and toxic chemicals. In this example, we are doing the avoidance. We are saying let's not have that intermediate at all, and that's pretty much what the next one would say. So that alternative 1 is where we don't have it at all, and alternative 2, we make we immediately make an easier to handle or a less dangerous chemical rather than the ethylene oxide. So yes, you just do, and the other thing that comes into this is a concept called designing for safety. It's called inherent safety in process design. Inherent safety, designing for inherent safety. So you always will choose a design where it is an inherently safe operation. In other words, there's nothing that can go wrong that could cause harm. And so that sort of is what heuristic 1 is talking about, is inherent safety in process design. Okay, so I can't write on the screen unless I start. No, I don't think I could write on the screen. So heuristic 2 is, let's consider using excess ethylene in DCE production. So here we said we need that much. We need stoichiometric amounts in our example of vinyl chloride monomer production. We had stoichiometric amounts of chlorine and ethylene. Chlorine is more expensive and it's valuable and toxic, and it's hazardous. So consider using an excess of ethylene. Let me get my pointer. There's my ethylene. Use an excess of ethylene, and therefore you'll still have ethylene coming into this reactor, and therefore you'd need to recycle that ethylene. And your mass balance would still be the same. And by recycling that ethylene, you'd recycle it right to the beginning here, you would have an excess of ethylene in the direct chlorination. And what that does is, from your kinetics, you've got your rate is proportional to, if it's elementary kinetics, the rate is proportional to concentration of chlorine and the concentration of ethylene multiplied together. You multiply the concentrations. K times the concentration of chlorine times the concentration of ethylene. And if you increase the concentration of your ethylene, you can keep the rate high even with low concentrations of chlorine. So having an excess of ethylene will keep the rate high and make sure that all of the chlorine gets used up. So as soon as you have an excess of the one component, it will push the reaction rate so that you have a corresponding decrease in the concentration of the other reactant at the end of your reactor. So that will be using up all of the chlorine, as much as possible of the chlorine in the direct chlorination. There is the separation. We separated it directly after the direct chlorination, and now you're putting in the excess of ethylene, and you make sure that you use up all your chlorine in that reaction. Heuristic 3. When nearly pure products are required, eliminate inert species before the reaction operations, when the separations are easily accomplished, or when the catalyst is adversely affected by the inert. Do not do this when a large exothermic heated reaction must be removed. Okay, so why do we say do not do this when a large exothermic heated reaction must be removed? Let's say there's an excess of water and that's an inert species in the reaction you're considering. You would want the water to increase the CP of the increase the heat capacity of the stream coming in, so that if there's a large exothermic heated reaction, the temperature doesn't rise as much. So sometimes it's useful to have an inert. But if the reaction's temperature is easy to control, then you would rather separate the water before it goes into the reactor, because it's often easy to remove water with distillation, and then you can get, because the water is already removed, you can actually separate to nice pure products. So because you don't have the interference of the water in the separation. Right. As an example, you've got A and B reacting, and they make E plus F. And if you've got an impure feed, you've got C or D. A plus C might make E. That's a byproduct. So you would certainly want to remove C, and D doesn't do anything in these reactions. And if it's easy enough to remove, then you would remove it. If this reaction is highly exothermic, then you would possibly want to keep D in. You need to decide whether to remove inerts, remove D, or after the reaction. So the ease of the separations must be assessed. This can be accomplished by examining the physical properties on which the separations are based, and implies the use of simulation. Your favorite simulation package, DWSim. All right. I'm just keeping an eye. Let me get onto. No, there are no more. There, Fransu. Nokia said, to practice, is that question 1 of old exam papers? Exactly. Question 1 of old exam papers will do exactly that. Some of those old exam papers, question 1, might involve the use of heuristics to get your flow sheet going. So I'm going to be asking you one that doesn't need a huge number of heuristics to get a flow sheet out of it. Luca, that's what is a large heated reaction? It is if you use an adiabatic reactor and the temperature goes up, I would say more than 200 degrees, that would be a large heated reaction, because 200 degrees in a reaction is so large that it needs to be controlled effectively, and that is pretty much why we're talking about large heated reactions. So look at an adiabatic reactor, see how much the temperature rise will be, and then make your decisions from there on your design. So we'll be doing many more heuristics. I think it's around heuristics 12, 13, 14. By the way, these numbers that I'm using in the slides differ from those in the book. I've picked out some of the heuristics out of the book to use in our lecture notes. Okay, so that was heuristic 4, was it? No, that was heuristic 3. So heuristic 4, introduce liquid or vapor purge streams to provide exits for species that enter the process as impurities in the feed or are produced by irreversible side reactions. Right, so let's think of our latest DWSim TUT. we had argon entering with the synthesis gas, the hydrogen and the CO. Where can that possibly exit that process if ammonia comes out as a liquid in the gas liquid separators? The only way to remove that argon is to put in a vapor purge stream. So the only time that it is not necessary to purge something, so either an impurity can enter as a feed in the feed, or it can be produced by irreversible side reactions. And irreversible is pretty much the important word there. If it's irreversible, it has to be removed somehow. It can't be. You can't push the side reaction to be reversible from back to the starting materials. And so it has to be removed, and the way to do it is a liquid or vapor purge stream. And that is only when these species are in trace quantities and are difficult to separate from the other chemicals. Yes, Philip, talk.
Prof, I just want to ask with regards to the DWSIM that we did last week. Why would we not try and remove the argon before the reaction, according to heuristic 3?
Yeah, because the boiling point of argon is going to be it's going to be less than minus 200 degrees C. So it's very close to absolute temperature. Now, how do you make if you're going to use distillation, for instance, how are you going to make a distillation column that's going to remove that argon? And by using a purge, the reactor is using up your hydrogen and your carbon monoxide and increasing the concentration of the argon. And so when you have your purge, you are losing some CO and hydrogen, but the recycle stream has increased the concentration of the argon because the other two components, CO and hydrogen, have been used up. So you've got a nice high concentration of argon going out of that stream. And then you can simply put up with the loss of your CO and hydrogen. Now, that doesn't mean that you're not going to recover the CO and hydrogen, but it is a much smaller stream. So if you use a membrane separation, which works nicely on a small molecule like hydrogen, you might be able to easily separate hydrogen, which is the more valuable chemical out of the two. You might be able to separate the hydrogen out of the purge stream. So you can further refine that purge stream. But for the main loop, it's good to use a purge. Right. So there's the ammonia synthesis loop, and it can be really difficult removing it from the feed material. So we put it into the loop. We're using up hydrogen and nitrogen in this reactor, and therefore the purge contains a nice high concentration of argon. Of course, argon is not going to dissolve much in the ammonia, and we saw that in the simulation. The ammonia was 99.99% pure as we took it off that loop. The purge flow rate selection depends on economics. We chose 10% split. So we said 10% is going off this way and 90% goes that way. And that 90%, this is shown as a pump, which is wrong. And this has to be a compressor because this will be a vapor phase loop. 90% goes this way, 10% goes this way. If we make this less than 10%, we are increasing the flow rate through this, and that means that the reactor has to be bigger because otherwise you'll have very high pressure drops, and the compressor, this recycle compressor, will have to be bigger because of the higher volume flow rates. So that is it is essentially economics. How much it costs for a bigger compressor, a bigger reactor, compared to how much hydrogen and CO you're losing with the argon in the purge. Okay. Next one, heuristic 5. Do not purge valuable species or species that are toxic or hazardous, even in small concentrations. Add separators to recover valuable species. So, if it's a valuable species, you will try and separate it in the loop, or add reactors to eliminate toxic and hazardous substances. So when I say purge, it means, let's just go back to the previous slide. It means that don't put that into the flare. So you need to purge to get rid of it from the loop. But instead of this being the purge, the one that goes to the flare, you will try and recover the hydrogen, as I was talking about. The hydrogen would be specifically a valuable species. CO maybe not so. So if you put in a membrane reactor, you can purge that, but the CO you would be able to put into your flare, and it will make CO2 in the flare, and well, that's not ideal that you're putting CO2 into the atmosphere, but it is not toxic at least. So let's talk about this purge and heuristic 5. So add separators to recover valuable species. So we said we'll add a membrane separator to try and recover the hydrogen, and the rest, the argon and CO, we will add a reactor, and that is a flare. The flare is simply a combustion reactor to eliminate the toxic and hazardous species, and that is CO. Okay, so in the ammonia example, we did both of these things. We added a separator to recover the hydrogen, and we added a reactor to eliminate the toxic and hazardous species. Another example, catalytic converter in a car exhaust system. You've got your engine. Let me get my pointer back. We've got an engine, car engine. We've got fuel and air in petrol and diesel engines. The air comes in excess, but when you make these combustion components, you will also be making carbon monoxide and NOx gases. And so the catalytic converter will convert the NOx gases into oxygen and nitrogen, and the CO into CO2 because there's excess oxygen available. So yeah, that's the purpose of a catalytic converter. It uses platinum in a honeycomb nanostructure. Well, it's maybe not nano. In a honeycomb type of structure, and that will convert all of these poisonous gases, CO and the NOx, and make harmless species. Heuristic 6. Byproducts that are produced in reversible reactions in small quantities are usually not recovered in separators or purged. Instead, they are usually recycled to extinction. So that is that's an interesting word. So what you are doing is to push up. If you've got, I wish I had the ability to write on the screen. So if you've got A plus B goes to C plus D. No, A plus B goes to C. And C is it's a reversible reaction, and C is not a desired product. You can push up, you can recycle the C and push up the concentration of C in the recycle loop. And that way you will increase the reverse reaction back to A plus B. And by increasing the concentration of C sufficiently, you can make the forward reaction equal to the backward reaction. And then there is no C being produced. So you'll notice in the past exam papers that I often have a reversible reaction as part of the reaction sequence. And then I will give you a rate, an equilibrium constant for that reaction. So the equilibrium constant actually says what is the ratio at equilibrium between the product of A and B divided the product of the concentration of C divided by the K equilibrium or Kc times the concentration of C divided by the concentration of A times the concentration of B. That is the Kc is equal to the ratio of the two. The ratio of the products divided by the reactants. So the Kc equals concentration of a concentration of C divided by the product of A, concentration of A, concentration of B. So let's just read that. Often small quantities of chemicals are produced inside reactions. When the reaction proceeds irreversibly, you must take those out because there's no way to push the backwards reaction. So small quantities must be purged. Otherwise, they will build up in the process continuously until the process must be shut down. When the reaction proceeds reversibly, it becomes possible to achieve an equilibrium conversion at steady state by recycling product species. And the key thing there is that A plus B goes to C. There's no C being produced in the process as a whole because it is at equilibrium. So even though there's a high concentration of C in the loop, there is no C being produced at all. So in so doing, it is often said that the undesirable byproducts, C, are recycled to extinction. Extinction being the net formation of C in the loop. I really wish I could write these reactions on the board to make it clearer. Don't know what's the matter with Blackboard up. Collaborate this morning. Okay. For competing series and parallel reactions, adjust the temperature, pressure, and catalyst to obtain high yields of the desired products. I'll tell you what, I'm going to stop. So I'm going to explain Heuristic 7 on the whiteboard. So I'm going to stop this presentation, which means I must go back here, share content, share application screen. No, how do I stop? Oh, there's a stop sharing.
Prof, I just want to ask a question about Heuristic 6.
Yes, sure.
Would you have to separate C out after the reaction? Otherwise, C is going to continuously be going out of the process, and then it's just going to keep on being produced. So would you have to separate it out?
Yes, you have to.
And then
so that it gets recycled. Yeah, you would. Yeah, exactly. You're right. Okay, so I'm looking for share blank whiteboard. Okay. So let's probably in CKN. You did this sort of reaction. Okay, you won't see it until I say enter. A goes to B, goes to C, goes to C. remember doing the kinetics for that reaction. And then, let me find the right tool here. A line. And another line. And a pencil. And a color. Now, let's look at the concentration of A. The concentration of A is going to start high and it will drop exponentially. So that's just a first order reaction. A starts high, and excuse the wavy line, but as the concentration of A gets less, the rate of reaction, which is the slope of the line, gets less. And this is the concentration of whatever species we're talking about. And this is time. Let's talk time and batch reactor to make things simple. And that is A. And now, let me choose another color. Now we look at B. And B is going to go up because at the beginning the concentration of B is low, but it's going up exponentially because A is creating B immediately. B is going up exponentially, but now as concentration of B increases, it starts converting to C because the rate of conversion of B to C starts increasing. So there's a maximum of the concentration of B, and eventually, given enough time, all the B will be converted to C. So that is B. And then, of course, now we look at C, and C is going to do C will not be much at the beginning. It will slowly increase, and eventually you'll only have C in your reactor. So let's say that the component that you want the most of, the desired component that you're trying to produce is B, and you do this in a plug flow reactor. You need to ensure that the residence time is such that your reactor is just this long, that the residence time equals that amount. Let's go with a line, a black line, and we say that is where you want to stop the reaction at that time. So that's how you put in the laboratory. You determine what that optimum time is. There's an optimum. As soon as you have complex reactions, there's an optimum. So now I'm going to go back to sharing the screen. Yeah, look at that. All right, I'm getting more skilled at this blackboard. So we're developing a base, obtain kinetics data, and check this assumption before developing a base case design. So let's have a look at this manufacture of allyl chloride. We're using propylene and chlorine, and we're making allyl chloride in the first reaction. No problem. That's great. The trouble is, there's a simultaneous competing reaction, K2, that makes dichloropropane, which is undesirable. But when you make allyl chloride, it reacts with the chlorine as well, with K3, and it makes dichloropropene, which is also an undesirable reaction, and HCl. So essentially, we want to maximize K1 and minimize K2 and K3. Let's have a look at the kinetic data. Heat of reaction, not not so relevant. K0, not so relevant. E over R is really important because that is how sensitive the reaction is to the temperature. So you can see that reaction 3, there, K3, that reaction is the most sensitive to the temperature changes. So if you push up the temperature, because the heat of reaction is negative, if you push up the temperature, it will occur quicker. This is the reaction 2, the undesirable reaction says you must use as low a temperature as possible. And unfortunately, the desired reaction is somewhere in between. So we can't just use a high temperature or a low temperature, we've got to use something in between. So let's just have a look at this on a Arrhenius diagram. And the red is the desired reaction and the blue is the undesirable reaction. Let me just get to that comment. No, reaction kinetics is something you only get by experiment, and therefore you've got to go and look in the literature who's actually looked at the rates of these reactions. So somebody who's been studying this set of reactions would have done experiments at different temperatures and deduced these values of E over R, which is the slope of these lines. Just get back there. Yeah, the slope of these lines is actually the E over, represents E over R. Right, so essentially you've got to choose an optimum temperature somewhere between a high temperature and a low temperature to maximize the production of your desired product in this case. And let's just see if we need to get the focus on the screen. What range of operating temperatures favor production of allyl chloride? And oh, that's the end of that. So essentially, when you do this, and I'm going back to the heuristic, I didn't see that in the actual, yeah, that's right, it's easier. So there's a theoretical, you can go and you can put your kinetics into a model and model your reactor and find out what would be the ideal size of the reactor to maximize your allyl chloride and what temperature to operate at. But in the initial distribution of chemicals, assume that these conditions can be satisfied. Obtain kinetic data and check the assumption before developing a base case design. So this is the thing about kinetics. Let's say you've got these rates, K1, K2, K3 from the literature. And the literature says, yeah, these are the numbers. But now in your process, you've got to recycle and you don't have quite the same initial distribution of chemicals. In other words, the feed composition is different in your base case design. Then you're going to get different results. And it may not be that these Ks actually still are valid. And that's why they say, assume that these conditions can be satisfied. In other words, this new composition of your chemicals coming into the reaction, and obtain kinetics data and check this assumption before developing a base case design. Because as soon as the distribution of the product chemicals, these dichloropropane, dichloropropene, and allyl chloride, as soon as that changes, it will change because there will be recycles. It's going to change the composition of the stream coming in. And then that assumption that you first made in your first design might be wrong about the best temperature to operate at and the distribution of the chemicals that will therefore come out of this process. So that's pretty much it. We're going to stop it at that point, and we'll go on to heuristic. Which one are we next at? We'll go on to heuristic 8 in the next lecture. So any questions? I'm going to stop the recording and take questions. Let me just see how I do that. Stop sharing. Yeah. Not as easy as I thought. Okay, let's try that. Yes.